So, ladies and gentlemen, we ended last class by doing what probably seemed like a very long problem to you. Okay? Well, it's fine if we want to differ on our opinions on that. But if you go back and look at your notes, what we were doing was a problem that involved a titration. Remind me what the word titration means. Acid plus base, okay? Adding an acid plus a base. And we were doing a problem where we had a set amount of acid and we were adding, as the problem went on, progressively more and more and more base. And we were calculating the pH at different stages, okay? And the key is, the combination, the titration that we were looking at was strong acid plus strong base, okay? And I've showed you this graph before, but I just want to remind you, this is what a titration curve looks like. It has this sort of S shape, okay? What's on the x-axis for this particular graph is volume of base being added. This is exactly like the problem we were doing. We're adding progressively more and more and more base. If you are doing a titration that is strong acid plus strong base, the pH at the equivalence point will always be 7. As we start to, like what we're going to do today, bring in something that isn't strong, like a weak acid or a weak base into a titration, then the pH at equivalence is not 7. Now let's just refresh our memories on what that term means. Moles of acid are equal to moles of base. Now what's happening over here on the right is basically the opposite situation. This would be a titration where I have a set amount of strong base and I'm adding progressively more and more and more strong acid. pH is still 7 at equivalence, but the graph is a mirror image of this one. And think about it, that should make sense to you. If you're adding more and more acid, shouldn't the pH be dropping? Say yes. Yes. Okay. Good. So what do if you have something weak in the mix? Okay, well, a lot of the process is going to be the same as what we were doing at the end of last class, with just a few other little added changes. Okay, so we are going to jump straight to a practice problem. Might I recommend that you get out some paper? As in any problem, if you have more than one of something, it's probably a good idea to list out your major species. But let's just read the problem first. Consider the titration of 100 mils 0.2 molar acetic acid. Stop right there. Strong or weak? Weak. It's got a Ka written right after it, so it's definitely weak. We're going to titrate this weak acid with 0.1 molar KOH. Strong what? Base. Good. This is a strong base. Calculate the pH of the resulting solution after the following volumes of KOH have been added. Blah, 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 blah. Okay. So, let's just start. All right. At the very beginning, let's think about what we have here. It's not that you have 0 of anything. You have 0 milliliters of base. No base, none, 0, zilch. So what do you have? You have acetic acid, and that's it. Nothing else. Think back. Think way back. How do you solve for the pH of a weak acid and nothing else? What kind of ice table? A Womex. Folks, this is what you did back in chapter 14. You had lots and lots of problems where you were given a weak acid and nothing else. Okay, fine. So if it's a Womex problem, what kind of reaction am I going to write out here? What are my reactants going to be? Acetic acid and water. Very good. Plus. I'm going to go ahead and abbreviate acetic acid as HAC. You are welcome to do the same. This is going to be like review. Okay? I'm not sure why I wrote water first. I usually don't do that, but it doesn't matter. We don't care about water. In a Womex problem, what kind of numbers are you putting into this table? Molarities. Okay, fine. Let's scroll back up. Acetic acid. 0.2. What about these guys? Are they present or no? No. This is like coming home to an old friend. Oh. Maybe not. Maybe that's just me. Okay? What kind of a K value do I want to set this equal to? How'd you know that?
Because it's an acidic reaction.
Okay, yeah. Your reactant that's being added to water is an acid. Do I have a Ka to work with? Yes, I do. How do I solve for X?
Well, you graph it and then find the intersection.
Very good. That's very nice. Okay. Don't worry about sig figs too much yet, because this is not my final answer anyway. How do I get to a pH at this point? Why is it okay to do that?
No, because H high.
What is
oxide
X?
is the same as
Yeah, because X is my H plus concentration. So yes, it is okay to just say negative log of this number. I'll save you the time. This is what you'll get. What do you think I'm going to ask you?
Does it make sense?
Okay, does it?
Yes.
How do you know?
Because it's close to, it's below 7.
It's below 7?
It's an acidic.
Yeah, it should be. It's just a weak acid and nothing else. My pH should be in the acidic range. Okay? So, would you need to list out your major species for that first step? You could if you wanted to. But typically when you only have one thing present, you don't really need to do that. But let me say this. If you did list out your major species at the beginning of this problem where there is no base, what would your major species have been? Water and what else? Acetic acid. 2 things, that's it. If you're looking for an acid plus base reaction, there's your acid, here's your base. Okay? But because water was one of the ones that you chose, it's a Womex problem. Okay? And that, ladies and gentlemen, is probably the biggest question I get in this upcoming test, whenever that is how do you know if it's a Womex problem or a Newman problem? If you're not sure, always list out your major species. If water is one of the things that you chose, then it's a Womex problem.
Always?
Always. If it's not, then it's a Newman problem. All right? So, first part done. Let's scroll back up. Now I'm starting to add some base. Now I have more than one compound present. Anybody want to make a suggestion? But even before that, list the major species. Okay, great. You already said water, acetic acid, what else? Now is present. KOH, no, wrong.
H plus.
Nope.
K.
K
Minus-
plus
Oh, hydroxide.
and
then
OH minus.
No.
That's it.
Is that hydroxide?
Yes.
Okay.
H plus is not one of my major species because where would it be coming from? But it's not because that's a weak acid. Okay, so I have 4 species to choose from. Let's see if this is a Womex problem or if this is a Newman problem. I'm sure you can probably go with your gut instincts here, but let's look in this list. What do you think if I'm trying to find acid plus base, is there an acid to put in there? What is it?
Acid.
Acetic acid. Okay. Is there a base?
Yes.
The king daddy of bases. Can you please tell me what my products will be? Water? Very good. And acetate. Okay. Is this a Womex or a Newman problem? It's a Newman problem. Water was not one of the reactants that I chose. So, what kind of numbers do you put into a Newman ice table? Okay, moles or millimoles, your choice. Let me scroll back up so we have numbers to look at. Let's deal with the acid first. What do I got? 0.2 molar and 100 milliliters. Okay, 0.02 moles or 20 millimoles. Okay, but if you don't like millimoles, 0.02 moles is just fine. Let's OH minus. Here's the volume. Here's the molarity. Give me a number. Moles or millimoles, your choice. Here's the molarity, here's the volume. Five what? 5 millimoles. Okay? Don't care about water. Just to make sure, if you're not sure if a number should be there or if it's a 0, is AC minus in my list of major species? No. That means initially, that's what I stands for, there was none of it. So that's how you can be certain if something should have a 0 or not. Okay. This is review from last class. What am I going to put on this next line? In a Newman ice table, what do you put on this line?
Numbers.
Numbers. I'm going to subtract on the reactant side and add on the product side. How did you know it would be 5?
That's limiting reactants.
Very good. My limiting reactant. Now this is where this becomes a little different from what we did last class. But you're going to love it. Okay? Oh, I guarantee it. Okay? Why did I say this is different from last class? Because, okay, last class, when we got down to the end of these Newman ice tables, first of all, water was our only product, so we didn't even look at our products. We only looked at these 2 columns. Well, now I do have a product to worry about. Here is what you need to do. This looks complex, it's really not. Think about what is it that you have left over here. Weak acid and some of its conjugate base. Say that again. Look at the two things that are left over. I have in the same container at the same time weak acid and some of its conjugate base. That is by definition something that starts with a B. A buffer. Okay? Remember, a buffer can be a weak acid and its conjugate base present at the same time in the same place. And here's the fantastic part of this. If you have a buffer and you need to find the pH, what can you use? Magic! No, wrong! Handy Haas. You don't need to do another ice table. You can use Handy Haas, which is awesome because it's quick and easy. So let's review a little bit. pH equals, you have the equation on your equation sheet. It said pH equals pKa. What the heck is that?
Log of negative log.
Negative log of what? The Ka, which was given to me. Plus log of base over acid. Please tell me which one of these things, HAC or AC minus, is my base. Okay? And the acid is? Yeah, acetic acid. Now, let me say something to you before you start doing number crunching. Okay? When we first started using this Hendy-Haas equation, and if you look on your equation sheet, this ratio right here has brackets around the top and the bottom. What do brackets mean? Molarity. Those aren't molarities. It's okay, because think about it. The molarity is taken from, let's use millimoles. Millimoles divided by milliliters. But for both of these, if I wanted to turn both of these numbers into molarities, I would be dividing by the same volume. They cancel out. It's okay to put moles or millimoles into that equation. That's perfectly legal. Okay? Calculate it out. This is what we get. And I want you to look at that number we just got and compare it to our first one. Why is the pH going up? Because we're adding base. It should be going up. Okay? I want you guys to do the next step on your own. Now, before you launch into this, is the equation going to be different? No. Same equation. Will the amount of acid be different? No. What will be different? The amount of base. Okay? You take it from here. Try this next one. Okay, anybody else get that number?
Yeah, that's.
Okay. Did any of you notice that this Hendy-Haas calculation was a little bit simpler than the one above it because, yeah, the log of 1 is just 0. Okay, hold on. All right. Ladies and gentlemen, this point in the titration has a name. We're not at equivalence. Very good. It's called the halfway point. Now, we saw that before. Let me refresh your memory on how you would even know that from the very beginning of this problem. Do you see that the acid, the thing we are titrating, the thing we have a set amount of, has been cut in half? Do you agree? You cut the number 20 in half, you get 10. If you are dealing with a titration where there is something weak in the mix, not only is it important to know when you're at the halfway point, but there's something special about this titration when you have something weak and you're at the halfway point. pH will always equal your pKa. Always. Think about it. If you're at the halfway point, the two parts of your buffer are going to have the exact same number, which means you're going to take the log of 1 every single time. Okay? I'm telling you right now, knowing this is going to be really, really helpful whenever we take our next test. Okay? Because sometimes you'll be presented with a problem where they will simply tell you right from the beginning, a titration has reached its halfway point. And then they're going to give you all this extra information that you're going to think you'll need to do a long problem. And actually, if you can just remember that fact, if they're telling you at the halfway point and you have a Ka value, that is a very quick problem. Over and done. Don't even need an ice table. Like, literally, if you are presented information and you can immediately see 20, 10, okay, this is going to be at the halfway point. You don't need to continue. You can literally write, as long as you do actually write something like at the halfway point pH equals pKa and then give the answer, that's great. You don't need to write it all out. Okay. Let's go on. The situation is going to change,
Yes.
but I want you to complete the ice table. You probably won't know what to do when you get to the end of it, but try it. Let's look at what we've got left over. Is it a buffer? No. A buffer needs 2 parts. 0, 0. I only have one thing left over. Okay. AC minus. Let's think about what that is. Is AC minus the acetate ion, is that capable of acting as an acid? Yes or no? Nope. Okay. Could it be a base? Yes, it is a base. Meaning, is it capable of accepting a hydrogen? Yes, it is. So, what you want to do, guys, at the end of a Newman ice table, look at the pieces you have left, or the one piece in this case. Ask yourself, what is it? That is a base. Is AC minus, the acetate ion, is that one of our strong bases? No. So it must be a weak base, right? How do you solve a problem? Go back like you're in chapter 14. How do you solve a problem when you have a weak base and nothing else? It's a Womex problem. Yes.
No.
Oh
Yes.
No.
Okay, so we're gonna Womex it. Cool. Now, for you, those of you that are true chemistry nerds, there is actually some part of this that is very cool. Feel free to disagree. Hold on, haven't even told you what it is.
But Nicole knows it's gonna be Nicole's like, no.
Okay, this first part was a Newman. This is a Womex. Let me show you something that's gonna blow your mind. Are you ready?
Oh my god.
Okay. We took the one thing that we had left over, which was a weak base. That was the only thing we had. How do you solve for the pH of a weak base? You Womex it. Add it to water. Did any of you notice, and I know that some of you did because I heard you say it, that the reaction I just wrote is the exact reverse of the one above it? Are you ready? We're going to take it to another level. Are you ready? Hold on. Hold on.
I don't know if I can manage this.
This is earth-shattering. Okay? People, what does equilibrium mean? You go all the way in one direction, and that's too far, so you've got to come back a little bit and settle. That's what equilibrium is, and we're doing it. We took it all the way in the forward direction here, but oh, wait, that was too far. So we've got to bring it back a little bit. Mind blown. Okay, now, guys, I will tell you this. This is as long as it gets. This is the longest type of calculation, okay? Notice that all of our other steps, we've only had to deal with one ice table. This is the only situation where you'll have two. And by the way, did anybody notice or remember the term when your acid and base amounts are equal? Ooh. We are at the equivalence point.
It's like the
Well,
perfect
all of these steps are at equilibrium, but this is the only one that you can really see it. Okay? But guys, an equivalence point calculation, I hate to tell you, is always going to be the longest kind. Okay? Now, here we go. Womex. Okay, great. Water's a reactant. What does the big M stand for? Molarity. Exactly. I don't have a molarity to put right here. How do you turn millimoles into a molarity? Divide by what kind of a volume? Total milliliters. So let's go back up here. I got 200 base plus 100 of the acid. Look at all that good work. Whew! That's why I like millimoles, because you can divide by milliliters, which most of your problems will be in milliliters.
Wait, why are we doing by 300? Oh, because you...
Total volume at this point. And this is my new molarity here. 20 divided by 300 gives me 0.067. I don't care about water. If you're not sure what to put here, this ice table is not happening until this one is finished. At the end of this first ice table, was there any HAC left over? No. Was there any OH minus? No. What do I put down here? X's. Hold on.
But it's acceptance or...
Oh, ho, ho.
Oh my god.
Okay.
guys are so smart. I love it. You caught it even before I said it. What kind of a K do I need here?
B.
A.
B.
There's some dissension in the ranks.
B.
Why
B.
KB?
Because OH minus
Okay, but a better answer would be, what is this doing? It's accepting a hydrogen. This is a base. Were we given a KB?
Oh.
No, I
But we
say
can
two.
do
Ah.
it because there's an equation for it.
You got
Yes.
it.
Science.
OMG. I was given a Ka value, so I can figure out a Kb, which I'll save you the time. This is what you get. 5.56 times 10. I'm running out of room. Times 10 to the negative 10th.
You have good handwriting.
Thank you very much.
Oh, thanks.
Okay. Now, what is this?
That's POH. No, sorry,
X.
the concentration.
Concentration
of
of, thank you.
Talking about POH.
Oh,
Yeah.
this is just awesome.
This is just like abusive.
Miss G, you like seeing people suffer.
I don't like seeing people suffer. I just have a twisted version of what's fun. Whew. Did the pH go up?
Yes.
Yes. Now, okay. There's something important to realize here. We're at the equivalence point. Look at the pH. It's not 7.
That's okay.
That is okay. You're right.
It's just
And
the
folks,
way it is.
think about it. Is this in the acidic or the basic range? Basic. Think about the two things that you're adding together. A weak acid and a strong base. Who's going to dominate?
Base.
The base. So even when their moles are equal, okay, it's like having equal number of people at the end of a tug of war rope, okay? Except the weak acid side has a bunch of like 8-year-old boys, and the strong base side has a bunch of bodybuilders. Okay, great. Each team has 5 members. I think the bodybuilders are going to win. Okay? Okay, the point is, the pH at equivalence should be in the basic range because you've got a strong base being added to a weak acid. Okay. There is one more step, which will not be this long. It is a little different, but I want to see if you can figure it out. You're smart cookies, you can do it.
Oh no.
I have 2 pieces left over. Is it a buffer?
Yes.
Nope.
No, never mind, it's not. But it's HAC and AC.
Oh,
No, no, no. I don't have any
base.
HAC left over.
Oh.
I guess it's not really.
So what are the 2 things that are
bases.
left over?
King Daddy.
They're both bases.
They're both bases. I have 2 different bases left over. What do you do when you're presented with a problem like you were back in chapter 14, where you have 2 of the same type of thing? What do you do? Go with the stronger one, and what do you do with the other one?
Throw it.
Throw it away. Ignore it.
But
Which base is stronger?
King Daddy.
The King Daddy. So guess what? you have an amount of OH minus and you can ignore that one. Well, okay, that's all fine and good, but I need a molarity here. How do I get that?
Well, just change it.
I've got an amount.
Wait.
Divide by what? I'm not looking for the number. What is that? Total volume, which is 350 milliliters. Which gives me this number, which I can turn into a POH to a pH. And there we go. Boom. Woo! That was great.
That was-
Okay. Now that I'm sure you have beautiful notes like mine in front of
More
you.
than that.
Okay. Let me say something to you. Listen. That I said to you last class. Are you going to be presented with a problem that's going to ask you to do all of this on a test or on the AP exam? Absolutely not. Okay? No. What they're going to do, which in all honesty I think is more challenging than doing all of this, is they're going to zero in on one of these situations. But you're not going to know which one it is.
So we still have to do all the work.
Correct. That doesn't mean you're going to have to do it for 5 different volumes. You're only going to have to do it for 1 volume. But you won't know, are you before the equivalence point? Are you at the halfway point? Are you at the equivalence point? Are you beyond the equivalence point? You won't know until you start working it out. And they're not going to tell you. Okay? I personally think that's harder. Okay? At least this way you've got a pattern to follow. But here's the take-home message, and then I'm going to let you try a problem on your own that's not going to make you do all of this. It's going to focus in on one part. When you are doing a weak acid, strong base titration, or a titration with one part that is weak, ladies and gentlemen, there are 3 possible scenarios, and we just did them. At the end of your ice table, you could end up with situation number 1. You have a buffer left over. What do? How do you find the pH of a buffer? Hendias. Okay? Situation number 2. You get to the end of your ice table. Let me scroll up so you can see it. And you don't have a buffer. You have only one thing left over. That is a Womix, a Newman-Denner-Womix problem. That's situation number 2. Situation number 3. You get to the end and you have 2 pieces, but it's not a buffer. It's 2 of the same type of thing. In this case, it was 2 bases. How do you know which one to go with? You go with the stronger one. 3 situations. Buffer, 1 piece left over, that means Womix it, or 2 things of the same type. 3 possible situations. So, folks, just chill out. Jeez, you haven't even read the problem.
Word wall.
Okay? This is not like the previous slide. This is taken from an old AP exam. Okay? Consider what I should have done here, instead of numbers 1, 2, and 3, I should have made it parts A, B, and C. Because all 3 are connected to the same problem. Okay? Is this problem going to have a whole bunch of different additions of base? No. We're focusing in on one part of it. Okay? Try it. This is an actual AP question. Try it. Any information you get from number 1 can be used if you need it from parts 2 and 3. Try it. I'm going to underline a very important term in number 1 that will help you.
Wow.
They're telling you you're at the equivalence point. That's a major hint.
Okay, so major species are HOCO, Na plus.
Here's another important word. What if I change it instead of original? Initial. If you're asked to solve for something initially, number 1 doesn't even need an ice table. They're not asking you for something at the end of the reaction. They're asking you something about the initial conditions.
Wait, initial
Now, you will have to do an ice table later, but you don't need it for number 1. Okay, let's just pause for a moment here.
Silence.
Okay? In number 1, I was told what the reactants would be. Acid and this base, which I split up because it was strong. And then they told us we are at the equivalence point. You need to think about what that means. Initial moles of acid are equal to initial moles of base. We were then told the volume and molarity of the base, which allowed me to solve for an amount of base. And if they're equal, that's the same number of acid. They wanted a concentration, which means a molarity. Now this is the part that throws people off the most, right here. Why didn't I divide by total volume? Because it's the original, yes, and that's true too. It was the initial concentration. These things have not yet been poured together. Okay? So I divided by the volume of just the acid. Okay? Now in number 2 and 3, what is the concentration of OCl minus ions and what is the pH? Now you need to do an ice table. Okay? So you take it from here. Okay. So guys, that is what a test question is going to look like. Okay? I'm not saying they're, you know, any less of a picnic than, you know, the last problem was, but all parts of this problem were at the same place. They were all at the equivalence point. It was just asking you different pieces of that one situation. Okay? The last thing I'm going to say, and then I will stop talking. How might these topics be covered in a multiple choice situation? Would they ever do this? No. No. You don't have your calculator in multiple choice. How could you do this without a calculator? You couldn't. But let me ask you a possible multiple choice question. What if you saw a question like, a titration is carried out between this acid and this base. What is the pH at equivalence? How'd you know that? Strong acid plus strong base, the pH is 7. You don't need a calculator to do that. How about you had this situation? And this time I'll give you some multiple choice options. Again, it would say, what is the pH at equivalence? Give you some options here. Why? Okay. But more importantly, what about this guy? Strong acid plus a weak base. Your pH at equivalence should be in the acidic range. Let's say you had acetic acid and KOH. Same multiple choice options. Correct. Now, is this in the basic range? Yes. But remember, equivalence point, it's not going to be at 14, okay? It's not going to be at a pH of 0 either. All right? You're looking for somewhere in the middle of the basic range, or in the middle of the acidic range in the previous question. Okay? I am done. I can hear your brain
I
sizzling.
figured out